In this lecture, we will be covering the topic of planes in R3, or three-dimensional real space. So the way we define a plane, or one way we can define a plane, is by having a point on the plane and a non-zero normal vector n, which is perpendicular to the plane. So if we draw a picture of what a plane looks like, something like this, hopefully we can see that if you have a point, we're calling it P naught on the plane, and you also have this vector that is perpendicular to the plane, which we're calling n, that these two things together define a plane. So we want to see how we can use a point on the plane P naught and the normal vector to the plane n to construct the equation, or an equation, to define the plane. And the first thing that we do in that regard is we pick a point P with coordinates x, y, z, and we call that just a generic point on the plane. So let P with coordinates x, y, z be a point on the plane. And let's think about what it means mathematically. Let's connect the point P0 and P with a vector, P0P. And we know that P is in the plane if P0P runs parallel to the plane. So P is in the plane if that vector P0P is parallel to the plane. But if it's parallel to the plane, think of it as thus: if you lie it down up against the plane, it will lie right on it. Then it must be perpendicular to n. So this means that vector P0P and n are perpendicular or orthogonal. Well, think back to how we determined if two vectors were orthogonal, and we thought of the dot product. So remember that two vectors, two non-zero vectors, are orthogonal if and only if their dot product is 0. Well, let's delve into that. So the vector P0P, remember how we do this, this will be the vector starting at the point P0 and ending at P. So we take the respective coordinates of P, and from them subtract the respective coordinates of P naught. So the first entry would be x minus, remember P naught had coordinates x naught, y naught, z naught. So the first entry in this vector was x minus x naught. Then we will have y minus y naught, and finally z minus z naught. N we had written as the vector a, b, c. And now putting these two together, we have our dot product result, and we substitute these in. So we have that x naught, x minus x naught, y minus y naught, z minus z naught, dot that n vector, ABC, must equal 0. And remember how we do a dot product. We multiply the x-coordinate values, and then to that we add the product of the y-coordinate values, and then to that we add the product of the z-coordinate values. And so when we do this dot product, remember again, n was this vector ABC, that dot product becomes a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And that dot product is what gives us what we call the scalar equation of the plane. So a scalar equation of the plane containing the point P naught and perpendicular to the non-zero normal vector n is given by this result here that we just derived. Let's look at an example. So let's find an equation of the plane containing the point P naught 102 with the normal vector n 312. And this is a direct application of that definition. We know the equation of the plane is this P0P dot n equals 0. And our P0P is, so we do x minus 1, y minus 0, z minus 2, dot product with that normal vector equals 0, which gives us 3 times the quantity x minus 1 plus 1 times the quantity y minus 0 plus 2 times the quantity z minus 2 equals 0. And there is the equation of our plane. We can simplify this if we want. 3x minus 3 plus y plus 2z minus 4 equals 0, or 3x plus y plus 2z equals, here we had a minus 3 and a minus 4, so that's a minus 7, add 7 to both sides, equals 7. And so this is an equation for that plane. And this is a good time to remind ourselves that linear expressions in x, y, and z represent planes in R3. Recall that when we did our discussion of lines, we needed parametric equations because linear expressions in x, y, and z don't represent lines. They represent planes. Another very common kind of example when dealing with planes is this type. So we're given 3 points. So 3 points that are not all on the same line uniquely define a plane. So in this case, we're given the points A, which is the point 5, 0, 0. So this point here. B, which is the point 0, 12, 0. And C, which is the point 0, 0, 5. And we're asked to find an equation of the plane through these points. So the plane we seek in the first octant, it intersects the first octant in this triangle here. So to find an equation for this plane, we need to build some things. We need to build some materials. So recall, in order to get the equation for a plane, we need a point on the plane and a vector perpendicular to the plane. We have 3 points on the plane, so that part's fine. But we need a normal vector. And one way we can do that is by building a normal vector from these 3 points. So for instance, let's think about the vector AC. That vector is parallel to the plane. How about another vector, AB? Also parallel to the plane. So AB and AC are both parallel to the plane. They are not parallel to one another, specifically because they form legs of this triangle. But recall a very nice result about the cross product. If we take the cross product of these two vectors, namely AB cross AC, the cross product of two vectors is perpendicular to both of those vectors, which means the cross product of these two vectors is perpendicular to this plane. So the normal vector we will define will be using this cross product. And using our right-handed coordinate system, this means the cross product in this case will point like this. And again, will be perpendicular to that plane. If you went the other way, AC cross AB, it would still be perpendicular to the plane but pointing downward. In either case, it works. So this is how we will set up our normal vector. So the first thing we need to do is create these vectors. So AB, so that's the vector starting at A and ending at B. So we subtract the respective entries of A from the entries of B. So 0 minus 5, 12 minus 0, and 0 minus 0. For AC, we subtract the entries from the entries of C, we subtract the entries of A. So 0 minus 5, zero minus 0, and 5 minus 0. And we now define n as the cross product of these two vectors. So n, which is AB cross AC, let's recall we set up our 3 by 3 determinant, where the top row are the unit vectors I, j, k, the second row are the entries of AB, and the third row are the entries of AC. And we break this down into the sum of 3 2 by 2 determinants. So the first 2 by 2 is multiplied by I, and we subtract the next 2 by 2 multiplied by j, and then we add the last 2 by 2 multiplied by k. And each 2 by 2 determinant is obtained by deleting the row and the column containing this coefficient. So we have, for I, we remove the first row and the first column, which leaves us with 12,005. For the second 2 by 2, we delete the row and the column containing j, which leaves us minus 5, 0, minus 5, 5. And for the 2 by 2 with k, we delete the row and the column containing k, and we're left with minus 5, 12, minus 5, 0. And now, to evaluate each 2 by 2, recall that you do this by multiplying top left times bottom right. So that first one would be 12 times 5 minus the product of top right times bottom left, 0 in this case. We then have minus j times top left minus 5 times bottom right 5 minus 0 times minus 5. And then finally, for the k coordinate, we have minus 5 times 0 minus 12 times negative 5. And so we have 60i, and notice here we have a negative 5 times 5, so that's a minus 25, but we have a minus 1, so plus 25j, and then we have plus k in here. This first term is 0, and we have minus 12 times minus 5, or 60. And so we can write this vector as 60, 25, 60. And we could use this as is, but if you want it to be a little simpler, you could factor out a 5. And you would get 12, 5, 12. And so this will be the normal vector that we use. And in fact, note, we don't even need to use that 5, because whether we multiply by 5 this 12, 5, 12 vector or not, it's still pointing in the correct direction. And then we choose one of the points, and any one of the points will work. So why don't we choose A, which was 5, 0, 0. So if we use this with A, then the equation of our plane will be, so we take the entries from our normal vector here. So we'll have 12 times x minus 5 plus 5 times y minus 0 plus 12 times z minus 0 equals 0. And again, we're merely using these two values here, our normal vector n and our point A, and we're using them as the equation we derive dictates for the equation of our plane. And in this case, we would get 12x minus 60 plus 5y minus 12z equals 0 as the equation, an equation of our plane. And so this really gives you some fundamentals to work with planes in space. And we'll see in some future material that we're going to look at lines and planes together, because we want to look at questions like, how do planes intersect? What's the distance between a point in space and a plane, which involves using lines and planes? These types of questions. So there will be more to come with lines and planes in conjunction.